Hey guys, have another lab here for you. This is going to be taking a look at endothermic reactions and exothermic reactions to show what happens to the temperature, but also to take a look at reaction rates. So I have all the ingredients set up for you, and I also have all the supplies and everything, and the actual labs may take about 5 minutes to collect the data, and during that time you'll be able to fast forward during those periods of time. So let me show you what I got. We have some baking soda. Here's some baking soda right here. And I also have 30 milliliters of citric acid. And we're going to be taking a look at what's going to be happening to the temperature during the duration of that experiment. The second experiment is going to be taking a look at hydrochloric acid, and it's also going to be taking a look at magnesium metal. So we're going to take a look at the temperature change in that reaction as well. One of these is endothermic and one of these is going to be exothermic, and we'll be able to tell by taking the final temperature minus the initial temperatures. So that's what we're going to be doing. I'm just going to set this here for now. What I need to do is I need to get the temperature probe ready, and so it's right here. And I also have this little setup here. It's styrofoam. Styrofoam is to help to retain the heat or prevent heat loss. And so it's just sitting inside the beaker just to provide some stability. I'm going to be taking the baking soda here, and then I'm going to be I'm adding it to the citric acid. And so here's the citric acid. I'm just going to put this in the cup. No reaction has taken place yet. This is just going to be sitting there monitoring the temperature. So what I have over here is I'll show you, and here is the computer screen. So the temperature is about 20.4. I'm going to go ahead and press collect, and then what I'll do is then I'll start adding it, and then we'll see what happens to the temperature. So that's going to collect, and I'm going to go ahead and add the baking soda. So we get lots of bubbling action. I'm going to stir this. So as I stir, I'm going to be also going to the graph and trying to get it perfectly scaled for us to see. And then I'll show you what's happening to the graph. So you can see that the temperature is dropping, and I'm going to keep stirring this until I kind of plateau. So take a look at the temperature. Temperature is about less than 2 degrees. So 1.7, 1.4, 1.5. Eventually it'll kind of flatline down at the bottom, and we'll get those temperatures. What's interesting is this is citric acid and baking soda. This is just Alka-Seltzer. So having Alka-Seltzer in water is going to drop the temperature. Wow, we're below freezing. Well, of pure water. So temperature is still dropping. This is going to auto scale, so the temperature is going to, or the scale will automatically change as we need. Temperature is at -1. I may need to do this for a couple more minutes until it stabilizes. So feel free to fast forward it because I'm just going to stir. Okay, so that's the lab. So what I'm going to do is I'm going to be stopping this. We went for about 200 seconds. We'll try to do the same thing for the other graph as well. What I want to do is I'm going to be highlighting this before and highlighting all this afterwards. And I'm going to be getting some statistics on here. It's going to give me my minimum, it's going to give me my max. So my maximum temperature was 20.3. So we can go ahead and record that on your labs. You can record it as the initial temperature right here. So the initial temperature was 20.3 degrees. The minimum temperature was 2.5, minus 2.5, minus 2.5. So when doing the temperature change, we're going to be taking the T2 minus the T1. Here's the T2 right here, minus the T1. When we subtract this minus this gives us a total temperature drop. It dropped minus 22.8 degrees for the duration of that experiment. Okay, I'm going to go ahead and print this off as well for comparison. And we'll get that later. We're going to go ahead and do the second part of the experiment now. So here is the hydrochloric acid. We need to allow the thermometer to kind of stabilize because it's been in that really cold environment. And we're going to be adding this piece of magnesium. I'm just going to try to break it into a few smaller pieces so it's going to fit nicely in there. And we're going to take a look at what happens with this. I'm also going to be resetting the graph. And we're going to try to have this go for a duration of 200 seconds as well, just to be consistent. So let me show you guys. Temperature's about where we started. Room temperature's about 20, so it's 19.9 degrees. And I'm going to go ahead and add the magnesium. And show you guys, whoop, we have to start this. Whoa. Okay, my bad. It started at 19.99, so that's going to be our minimum temperature. And this is going to be going up like this. So I'm going to just kind of stir, stir, stir. Okay, so you can see temperatures going up. We're going to try to do this for a period of 200 seconds, so that's going to be another 3 minutes. So at this point in time, you guys can go ahead and fast forward when I stop. Just going to sit here and stir, stir, stir. Okay, so it has actually plateaued, and we'll go ahead and we're going to stop this. You can see what's happened here. Okay. I didn't let it go for all of 200 seconds, but we can see a difference between these two. Again, I'm going to press the stat button, and that's going to give me my minimum and maximum. So I'm going to start from down below, go all the way to the top here, and press the stat. Remember, our starting temperature, the initial temperature was 19.9. The final temperature went up to 37.5. So we're taking this minus this, and let's get my calculator. We have 37.5 minus 19.9. That gives us 17.6. So that's the result. Let me go ahead and print this off. And we can use these as comparison. So here's our first experiment, and I'd like to sort of graph what that looks like. And then we also have the second one, which looks like this. Okay, so again, the first one looks like this. We're going to kind of sketch this. Okay, and we're going to sketch this down below here. You can create a little XY axis and another XY axis for the other one. The temperature is going to be on the y-axis, and the time is going to be on the x-axis. So we're going to just sketch this, and it drops off really rapidly and then goes like this. Okay. Second one, we have a gradual increase in temperature. It looks something like that. So this says calculate the delta T. We calculated that, and we subtracted those two. So we've already done that. So which reaction of these is exothermic? Which one is releasing heat? Well, remember the first one got colder, and this is the second one, and we're taking a look at the delta T, the change in temperature. This dropped 22 degrees. This increased by a factor of 18 degrees. So this is the one that increased right here. Which is exothermic, which releases heat? This is the one that releases heat because this is the one that increases in temperature. So I'd like you to write that. Which part is exothermic? It's part 2. What's the evidence that you know that is exothermic? The temperature increased. Remember, exothermic is heat going out. Heat was released and the temperature increased during the duration of this. Which reaction had a negative delta T? This is part 1. Is this reaction endothermic or exothermic? We can say that it is endothermic. It's the opposite of an exothermic. What happened to the temperature? For an endothermic reaction, the temperature is going to decrease. It feels colder. It gets colder. It actually pulls the heat from the surrounding environment into the chemical reaction, and therefore it makes the surrounding area cooler since it pulled the heat to make that reaction take place. For each reaction, describe 3 ways that you could tell a chemical reaction was taking place. Did you guys see anything during the duration of that? You can actually still see it right here. You might be able to hear it. There's bubbles. Okay, what's taking place in the other one is bubbles was taking place in the other one. The hydrochloric acid completely dissolved the magnesium. So chemical reactions. This is from last semester. Bubbles is an indication that a chemical reaction is taking place. What happened to the magnesium? We can tell a chemical reaction has taken place if there is a visual change and the magnesium disappeared. Those are some pieces of evidence that a chemical reaction took place. Also, a change in temperature. Change in temperature is an indication. So let's take a look at these. For the part 1, we have a negative delta T. Part 2, we have a positive delta T. Negative delta T means it got colder. Positive delta T means that it got warmer. If it gets colder, let's do the other one. If it gets warmer, this is the easier one. It's an exothermic reaction. If it gets colder, it's an endothermic reaction. Okay, with an endothermic reaction, heat is pulled in, making the surrounding environment cooler. Exothermic reaction, heat comes out. The temperature increased, the heat's coming out. Heat goes in, the temperature is decreasing in the endothermic reaction. Last part is which reaction took place at a greater rate, meaning which one took place faster? Well, this one went for a longer period of time. This one sort of bottomed out. It's not really looking at how long the duration of each of these took place, but it's taking a look at the slope. If you take a look at this part right here versus this part right here, most of the reaction took place within this duration of time. The reaction took place during this duration of time. So this chapter is also taking a look at reaction rates. So in the case of the first one, here's the first experiment, the slope is going to be steeper. If you have a steeper slope, what's going to happen? Imagine you're standing or rolling down that slope. You're going to roll down a lot faster, or a ball will roll down faster. We have a steeper slope, and so what happens is it goes faster. Let's take a look at the second one. The second one, the slope is more shallow. What does that mean? It means that the reaction is taking place slower. So here's the question. Explain your answer. Which took place at a greater rate? This took place faster. Question is, why? I started off with baking soda, a powder, versus the magnesium, which was a solid metal strip. Can you guys see where this is going? We have a powder versus a piece of magnesium. How will powder react compared to a solid piece of magnesium? It's going to react slower or faster? It reacts faster. Why? When you're in powder form, you have smaller pieces. And remember, reaction takes place on the surface of things. So you increase the surface area. When you have one giant piece, you're actually decreasing the surface area. If you increase the surface area, you create more places for the reaction to take place. It's going to go faster. When you remove those, the reaction will go slower. So to summarize, this lab was taking a look at both endothermic and exothermic reactions. Endothermic reactions decrease temperature, they get colder, and the heat is going into the chemical reaction. Exothermic reactions are opposite. Exothermic reactions are warmer, they increase in temperature, and the heat comes out. And we also took a look at the rate of reactions. This first reaction took place much more quickly because it was in the powder form. It was smaller, more surfaces for the reaction to take place, for the collision theory. The second one had a single piece of metal or a couple pieces of metal. We decrease the surface area. And so what happens there is that there are fewer surfaces to react, and therefore the reaction is going to take place much more slowly.